Hello and welcome. In this video I'll be covering section 5.3, which is over logarithmic functions and graphs. My goal for you by the end of the video is to be able to find common logs and natural logs with and without a calculator, to be able to convert between exponential equations and logarithmic equations, to be able to change logarithm bases, as well as graph logarithmic functions. So, thus far in this chapter, we've talked about inverses to start, which was swapping x's and y's, as well as exponential functions and their graphs. So what we're going to talk about is kind of the combination of those two concepts, which is what is an inverse of an exponential. So let's just start with first thinking in terms of what would an inverse really look like for an exponential. So if I just said, let's make a table for f of x equaling 2 to a power of x, plugging in -1, 0, 1, 2, and 3 should give me enough points that I can safely graph this. So -1 would turn into 1/2, 0 would turn into 1, 2 to the power of 1 is 2, 2 to the power of 2 is 4, and 2 to the power of 3 is 8. So if I were to plot each of these points on my grid over here, -1, 1/2 would be right about there. 0, 1 is there, 1, 2, 2, 4, and 3, 8 would create this graph. Remember again, it has a horizontal asymptote of the x-axis. So I could maybe draw that on here as well, or that would technically be y equals 0. And what this wants us to do is come up with a t-chart for the inverse, which we don't really necessarily know what that would be, so I'll just notate it with the f inverse notation. Ultimately what I should do is just take the x's and y's from my exponential graph and essentially swap them. So -1, 1/2 would now be 1/2, -1. 0, 1 would now turn into 1, 0. 1, 2 will turn into 2, 1. 2, 4 will turn into 4, 2. And 3, 8 would turn into 8, 3. And since I'm swapping x's and y's, notice my asymptote, if I were to replace that with an x, or swap the y that was there to x, that actually creates a vertical line, which is now going to be a vertical asymptote. So if I were to now graph these points on my grid over here, I've got 1/2, -1 would be right about there. I've got 1, 0. I've got 2, 1. 4, 2. And 8, 3. And notice this one, instead of having a horizontal asymptote, now has a vertical asymptote. That would be the y-axis. So I'd get really close to that and then start curving to the right. And if you think back to why should this make sense, graphically this should be a reflection across the y equals x line, which if I were to sketch it on here, y equals x, notice it does look like a mirror image of one another. So what is the type of function that we just did? Well, we were able to graph it without really necessarily knowing what it was, just by swapping the x's and y's of this exponential function. But what that actually is called is a logarithmic function. And we'll talk a little bit more in depth about what that looks like and how that works in the remaining part of this lesson as well as next lesson. But hopefully it seems reasonable that because I have this function that's exponential, there should be something that's inverse of it, because after all it does pass a horizontal line test. It's just going to create a new type of function that we have not really had much experience with. But hopefully this video will help it make sense as to how those work and where they come from. So now that we kind of have an idea of what the shape of a graph would look like for a logarithm, or the inverse of an exponential, let's go ahead and actually physically define it. So if we think of an exponential equation, which would be in the format of y equals some base raised to a power x, where again notice the x, or the input variable, is up in the exponent area. Remember, when it came to finding inverses, what I would do is swap the x's and y's. So if I swap the x's and y's, that actually would turn into now x equals b to a power of y. And normally what we would do is then try and solve for y, but this would be where we kind of get stuck because we don't necessarily have or know what a inverse of an exponential is, other than what I've just said here earlier, which is called a logarithm. So to kind of define this, it happens to work out such that if x is equal to b to a power of y, to isolate y, we introduce a concept called a logarithm. And technically how we would say this is y equaling and this would be log base b and then of x. So just to try and at least get out in the open, how do I even say whatever that function is? Whereas before we were able to say it's b to a power of y, so we had a statement for it. Now we have the ability to say this log base b, where notice the base b part actually is like a subscript. So if you remember what superscript and subscript are, superscripts are like the exponent area, so it's a kind of smaller font and then raised, whereas a subscript is essentially a smaller font but dropped. So this would be subscript. If I finish my thought, sorry. And then it has the inside, which would be where this parenthesis part is. So all logarithms kind of have this fill in the blank of y equals log with some base underneath it and then some actual inside to the logarithm. So we would need to know what our base is and then what number is inside. It never can be empty. In other words, we can't do something like log plus 4. This would mathematically make no sense because there needs to be something inside of the log in order for that to really work. So saying something like log plus 4 or divide by log doesn't make sense, but if I said divide by log of 5, we could do that. We'll talk about here shortly what that means if there wasn't a number in that little subscript area. So again, notice it's a subscript here, and then this would be considered the inside of the actual function. Now when it comes to comparing the two types of functions we're talking the most about, the exponential and logarithmic, the inverse relationship that they have. Ultimately, we talked about in the previous video kind of some of the properties of the graph, such as the base needs to be greater than 1 if it's going to increase. If it was less than 1, it would decrease. But essentially it would be something that's continuous. It happens to be 1 to 1, hence why it has an inverse. The domain is actually all real numbers for the exponential, but the range was only all positive real numbers, so everything above 0 but not including 0. It was always increasing when b was greater than 1. It was when it was between 0 and 1 that it would be decreasing, remember? And then it also had a horizontal asymptote that was the x-axis, or we could also write that as y equals 0, if that helps. And then it had a y-intercept at 0, 1. And it never actually touched the x-axis because of that horizontal asymptote, so there was no x-intercept. And then some of the key points we talked about as well, the -1 and the reciprocal of the base, 0, 1, then 1 and whatever the base is, and 2 and whatever the base is squared. And we could plot those points and create a graph that looks similar to what's there. Well, a logarithm, as you could hopefully gather from the previous example here, is now it's x equaling b to a power of y, which we actually notate that with log base b of x. And since it's an inverse relationship with the function f that we defined with the exponential, we could say that this is the inverse function of f, or f inverse of x, representing log base b of x. In this case, we're using an example where b is greater than 1. The stipulations is the b does still need to be positive and it cannot equal 1. But if that base happened to be something that was less than 1, then I would expect this graph to kind of be a little bit more upside down, or it would look something maybe like that. Notice that would decrease, and it hopefully makes sense because if the exponential was decreasing, its inverse also should decrease. But anyway, for this one, we're just talking about the increasing example, so the base is greater than 1. It just needs to be any real number, so long as it's greater than 1 for this example. Notice it is still continuous, meaning you can draw it from left to right without stopping or jumping or skipping anything. It does happen to pass the horizontal line test, so it would be 1 to 1. But if we look at our graph now, the domain is 0 to infinity, where I don't include 0, which, again, if you think about how inverses work, what was the range of the original function became the domain of this inverse function. So notice the range with the exponential was 0 to infinity without including 0. That now is my domain. Then, with an exponential, the domain becomes the range of its inverse, so hopefully it makes sense that the range of this is actually all real numbers, or it goes down forever and up forever. It goes down a lot faster than it technically goes up, because as you can see, it kind of does start to slow down, and it actually takes a lot further to the right for it to become a very large number, at least as a y value. It is still increasing, as you can see. It's coming up the page from left to right. But now, instead of having a horizontal asymptote, it has a vertical asymptote, which is the y-axis, or you can say it's x equals 0. And what that basically means is as I approach that 0 from the right, so this notation with this plus sign right here, that just means from the right. So the right side of 0, as I get closer and closer to it, the actual y value of this function gets closer and closer to negative infinity. So it spikes down super fast as we get close to 0, in other words. It does actually now have an x-intercept, but does not have a y-intercept, and that x-intercept happens to be the swapped ordered pair from the exponential that now would be 1, 0. So just like we talked about with x's and y's swapping, all of the key points that we had from the exponential, I could just switch their orders, and that would be some key points for our logarithmic graphs. So really, when it comes to making a t-chart, it almost is better to think in terms of what would be a good y, and then try and figure out what the x would be based upon that. So you could utilize this top part with the x equaling b to a power of y. You can make a t-chart by selecting y values, which is a little bit backwards, but just plug those in, and that would give you what their corresponding x value is if you really needed to make a t-chart. Now, when it comes down to it, really what we're doing is if you think of how I just described doing a t-chart, where we actually would be getting y values, or it would be easiest to think what y value do I get. All of these, when it comes down to it, is really just thinking what power, if I put it on the base, would match the number that's on the inside. So you could really kind of treat this like, let's just solve for the variable, set it equal to x, so it's really 10 to what power is equal to 10,000 for this example, which I could then rewrite if this is 10 to the x equals, if that's 10,000, that would be 10 to a power of 4. So in this case, x would just equal 4, because that's the power on 10 I would need to put in order to make it equal 10,000. We could do a similar statement with this next part and just say, okay, if that's set equal to x, that's my unknown. This really is like 10 to what power is equal to 0.01. Well, 0.01 really is like 1/100th, which if I wanted to rewrite that, that would be the same as doing like 1 over 10 squared, which again I could rewrite and just say that that's really like 10 to a negative 2 power. And now that I have the bases kind of matching, hopefully it would seem reasonable that the two exponents, x and negative 2, should match. So this particular one would equal negative 2. So notice the answers for these logarithms are the power that I would put onto the base in order to make the number on the inside happen. So if I think in terms of 5 to what power is 125, I could say something like 5 to the x equals, and then 125. Well, 125, if we think of it, it really would be 3 5s multiplied together. So this would be 5 to the x should equal 5 to the third. So that tells me that the value of this one should just be 3. Next one, it would be 9 to what power is equal to 3. Well, if we think in terms of what is 3 the same as, well, I could think of this as really like 3 is the square root of 9. So if I said 9 to a 1/2 power, that would equal 3. So that kind of tells me in this case that the x should equal 1/2. So it's kind of more in this case comparing these two right here. Because the square root of 9 is 3, we could then say that the result of log base 9 of 3 should be 1/2. Next one's a little bit easier. 6 to what power is equal to 1? Well, the only power I can put on something and get 1 back is 0 itself. Remember, anything to a power of 0 is equal to 1, so kind of the moral to take away here is anytime you take a log of 1, doesn't matter what the base is, the value of that logarithm would be 0. And then the last one, it's going to be 5 to what power is equal to 5 itself. Well, that should just be a power of 1. That's the only way that the base would not change into a new number. So kind of what to take away from this one, or as far as a property that this is really kind of exploring, is anytime the base matches the number that's inside, it just leaves a value of 1 as a result. So this slide is really just pointing out the last two statements, or the last two examples I worked through, and kind of something that's obvious. Anytime the base is presented, it really doesn't matter what the base is, so long as it's not equal to 1 or a negative number. So log base b of 1 will always have a value of 0, no matter what the base is. So even log base 7 of 1 or log base 24 of 1, all would have a value of 0. Anytime the base matches the number inside, like the last example on the last slide, it will just turn into a value of 1. So those are just a couple of nice, helpful things when it comes to trying to simplify or evaluate some of these logarithms that we can take advantage of. Now, as far as another thing that we're going to do quite a bit of is the ability to convert back and forth between what would be exponential form compared to logarithmic form without having to show all of the algebraic steps as to how that happens. What's nice is in both of these scenarios is the base is called a base. So remember, this is log base b of x is y, whereas the second one, it's x is b to a power of y. So it's a base of b, well, not in, but is. But again, the base is still called a base, so that hopefully makes the conversion a little easier. Then the other way to think of it is what's inside, so in this case, what's inside the log will become outside or by itself. And then what's outside by itself in log form becomes what's inside the exponential. So if you just kind of think, okay, the base stays a base, but then what was inside is by itself, and what was by itself now is inside. Hopefully you can kind of see how these things will kind of interact, where the x that was inside turns into an x by itself, and the y, or the number that it was equal to, will turn into the y that would be inside. So those two kind of key things as far as their location is concerned is once that kind of gets solidified, it becomes a lot easier to be able to do these conversions. And that'll be kind of what the next examples will work through, is just showing you how this conversion forwards and backwards really works. So this example is just going to explore one of the possible conversions. So notice all three of these expressions are presented in exponential form, and it's saying that I want to convert it into logarithmic form. So identifying what our base is usually a good start. So in this case, I see a base of 2 for part A. So that means I'm going to have log base 2. Again, I'm making that 2 a subscript. Then it will be of something. You don't have to necessarily put parentheses, but when we're starting out, it might be beneficial to think, okay, there needs to be an inside, so I'll open a parenthesis and then close it. So whatever was by itself, which in this case should be the 16, now should be inside. So it's going to be log base 2 of 16, and then it would equal what was inside the exponential now needs to be by itself, which in this case should just be the x, or whatever was up in the exponent area. We did a similar thing with part B. Notice our base of the exponential is 10, so this is going to be log base 10 of whatever is by itself, which in this case the part that's by itself is this 0.001, or 1/1000th. So again, I'll open a parenthesis just to kind of distinguish there is truly something in the logarithm itself. And then it would equal whatever had been inside. Well, what was inside the exponent area was -3, so that's now going to be all by its lonesome. And so I've got log base 10 of 1/1000th would equal a -3. Then this last one, introducing or kind of exploring the concept of e, which we introduced last class. Again, e is just a constant, the 2.72-ish number, called the natural number. So with this one, it's going to be log base e of what was by itself, so of 70, and again that's inside of the logarithm, and then that would equal whatever was inside, which was a power of t, so now t is all by itself. So each of these, as you can see, I'll go ahead and box them up just so they distinguish themselves a little bit from each other. But those would be my three results of just converting from exponential form into logarithmic form. Now this second two that we have, the log base 10 and the log base e, we'll talk about a little bit more in depth. They actually have a little bit different notation than what I currently have, so me writing it that way for me is a little bit weird, but I'll leave it for right now just so you can kind of see how the base gets involved with the logarithm as well as what's inside and what's by itself. Now going the other direction, notice all three of these are now presented in log form, and it wants us to express the result in exponential form. So once again, we just start with what is our base. So in this case, our base is 2 for part A, so it's going to be 2 raised to some power, so whatever is by itself, which in this case is 5, is going to become the exponent. Then it will equal whatever had been inside, which was a 32. So I don't know if that's any easier to kind of distinguish each of those parts when it's in logarithmic form converting into exponential, but hopefully it's at least making sense where each of the parts go. The base is still called the base. What was by itself goes inside, and what was inside goes by itself. Moving on to part B, even though I have variables involved, no big deal, I still can evaluate it. So this one has a base of A. What was by itself was 8, so that's now going to be inside this function, so that's the exponent, and then it would equal what was inside was Q, so that needs to be by itself. So each time if you just kind of say things in your head the same way I'm saying them out loud, hopefully it will make sense how you organize it and where the parts need to go. The very last one, even though the log is on the right side of the equal sign, it's not going to change a whole lot. I'll start with my base. My base is t. What's by itself is x, so that's now going to be inside, and then it's going to equal what was inside, which was m. So we explored a little earlier how to compute logarithms if I didn't have a calculator, and what we did kind of have to have is the number inside needed to be some version of whatever the base was, so I could try and figure out what the power was. That's not necessarily always going to be the case. So the thing that's kind of nice about calculators and how they're built is most calculators do have the ability to do two main logarithms, the first of which is what's called a common logarithm. And hopefully it seems reasonable if you think of how our number system is based. Our number system is based upon 10, so if you think of like money, you have ones, then tens, then hundreds. But then even when you talk in terms of like decimals or pennies, you have, the 10 spot as well as the 100th spot, but everything is always base 10 in relation to the previous value. So since our number system is based on base 10, it was common enough, hence the name common logarithm, that anytime you don't have a base written, such as this where it just says log of x, this is implied to be the same as saying log base 10 of x. So it's kind of similar to like square root symbols. Square root symbols, technically we don't write the 2 as the index just because it was so commonly used or utilized in math that they just decided to kind of bound together and say, if I don't see a number on a radical, I'm going to assume that it's got an index of 2. Similar thing is happening with logarithms here. If I don't see a number as the base, then the implied value is a base of 10. And again, that has to mainly do just with how our number system has been built. So when it comes to actually computing these, most calculators that are scientific or higher should have a button that just lets you do a log base 10, and it actually is just a button that says log. So to kind of show how this would work, I do have the ability to project up at least a replica of what calculators you guys use. So with this first one, notice the log button is right next to the 7 over here on the far left. So if I just go ahead and press log, it will just open up a parenthesis right afterwards. And with this one, if I go ahead and switch back to it, it's going to be log of 645,778. So it'll just be 645,778 inside. And you don't necessarily have to close the parenthesis, but good practice, I guess, is to go ahead and close it. So notice the parenthesis to close is right above the 9. And if you press enter, in this case, it gives us 5.81008. So this says to round to 4 decimal places, so it'd be 5.8101 for this first example. If we bring it back up for the next one, notice again all I have to do is just press log, it opens up the parenthesis, and then 0.0000239. And close the parenthesis, press enter. This one comes out as negative 6.6216. Hopefully I remember that one right. 6216, yep. And then the very last one, log of negative 3. Notice what's going to happen with this is technically that would be what base raised to a power equals a negative number. If you think of how exponential functions work, this should be a problem because the graph of an exponential is always positive. I can't really get a result that comes back negative. So when I press enter on this one, it's actually going to tell me some form of error. So anytime you get an error with logarithms, either you haven't typed it in right or you're trying to evaluate a number that it actually cannot equal. So you can also think of the graph of this. There were no x values that were allowed to be negative, so this is basically just telling us, okay, since this was non-real, this actually has no value or no solution. Or you could even say it's non-real. Now we're not really going to ever worry about trying to solve for what would be the base or what would the value of this be, 10 to what power would equal negative 3. That's a completely different type of math that we're not going to explore, but just what we can take away from that is I should never ever ever have to worry about plugging a negative inside of a logarithm. If you ever attempt it, it's going to give you something that tells you, okay, hey, there was an error, mathematically speaking, I can't get a real solution. And so that's our conclusion at the end, is we would just say something like no answer or no solution. Now the other type of logarithm that most calculators from scientific level and above have is what's called a natural logarithm. So a natural logarithm gets involved with a lot of exponential growth ideas, or technically there's also an idea called logarithmic growth. But with this, it's going to be a base of e. So remember, e was that number that was approximately 2.72-ish. It technically continued on forever and ever and ever. It was like really 2.718281828, and then it kept going. But as far as how do we actually represent this, well, log base e, which we had come up a little bit earlier, is actually the button on your calculator that says ln. So it looks like in, but really this is an L followed by an N, which if it helps, you could think logarithm with natural base as why it's called ln. So on the calculator, it should just be a button, at least with our calculators, if I go ahead and bring it up. So I've got the same number, 645778 as my first example. So I'm going to go ahead and quit out of this, so don't have to turn these off. I don't know if you've ever seen this, but second of mode right above it, notice it says quit. That takes you back to the main screen. I'm going to go ahead and clear all of that stuff out. But with this one, notice the ln button is the one that's actually directly next to the 4, or right underneath the log button that we were just pressing. So if I go ahead and press it, notice it's now the red button, just to kind of show you where it's going to exist on the calculators in class. And this first number, what was it? 645788, or 778, I believe. I'll double check it here in just a second. Close the parentheses just like before. This one gives us its 13.3782. Which 645,778. Let me double check. Yes, I did remember it correctly. Sweet. The second one here, again, this is just more practicing, just being able to plug things into a calculator. And then the last couple we're going to talk about here in just a second, but this one would just be the natural log of 0.0000239. I think that's the same number that we just plugged into the common log, and we got a completely different result. In this case, it came back negative 12 point, and then 9442. Natural log of negative 5, if we think in terms of what just happened when we did a common log with a negative number, this one should come back with an error as well, because again, I cannot plug a negative inside, so it just kind of confirms that when we plug it in. So this one has no solution or no actual value. It's a non-real solution, I guess is another way you can say it. Then the last couple, the natural log of e, if we think back to one of the properties that we had before, that should just equal 1, but we can just double check it with our calculator here. Natural log of, and then to get e, it actually exists in a couple of different places. So in this case, it would be the second of the divide. Notice that gives me the e value, but this really should just come back as 1 because the base matched what was inside. And then if we think about the next example, what's the natural log of 1? Well, it doesn't matter what base I have, any log of 1 should equal 0, which calculator confirms. So with this one, I got 1 for our first one and 0 for the second one. And no, I don't need to add decimals and put 4 extra zeros just because it says round to 4 decimal places. Anytime it's a whole number, you can go ahead and just write that whole number down without worrying about the decimal part. So again, just to remind you, those last ones, even though it was the natural log, some of the properties that are helpful is if I have 1 inside, I know the value would be 0. And if I ever have just plain e on the inside, it would be 1. With common logs, that technically would also hold true. I could say that log of 1 without a base written implies again that the base would be 10. I know that that would equal 0. And in this case, log with 10 inside, since the base was not written, I would imply that to be a 10. That matches the number on the inside. That would equal 1. So that works with both the natural logs as well as the common logs. Now with regard to how do I deal with all other logs? What if I needed to do, like, say, log base 2 of a number or log base 5 of a number or whatnot? We do have the ability on scientific calculators and graphing calculators to, I guess, do those. The graphing calculators, a lot of the newer ones, have the ability to actually fill in the blank with a base value, and if you leave it blank, it implies that it would be a 10. But anyway, when you press that log button, if you notice that it doesn't give you the ability to change the base, we have what's called a change of base formula, where essentially what we do is we pick whatever logarithm we want to switch to. So the two ones that normally we would do is either the common log or log base 10, or the natural log or the log base e, because those two buttons exist on our calculator. So some of the problems that you'll have will just say, go ahead and convert this specifically into common logs or natural logs, and then you just have to adjust accordingly. But basically what happens is the base of the original logarithm, so if this was like log base 2, I'd end up doing whatever log I want to switch to of that base. So notice the base went into the inside of a logarithm in the denominator, and then whatever was inside the original logarithm goes to the numerator, and then whatever log I want to switch to is what I use on top and bottom. So I could rewrite this as it would be the natural log of m over the natural log of b, or I could also write this in common log format, which would be log base 10 of m. I guess I didn't throw parentheses. Just to stay consistent, I will. Over log base 10 of b. But notice again, the base goes to the bottom. That's the way I always remembered. And then whatever was inside just goes in the other spot, which the only other spot would be on the top. But notice I used the same log on top and bottom to do this change of base formula, which we'll practice a couple of examples of here in the next slide. So this first example, it says we want to convert to common logs. So it does say use the change of base formula to change it to the indicated base. In this case, with it saying common logs, that means I want to switch to log base 10. So again, whatever the base is going to go to the bottom. So I can go ahead and maybe set this up where I just go, okay, common logs, let's do common log of the base on the bottom. And then whatever I haven't used yet, which is the 8, needs to go on top. So it would be the common log of 8. And at that point, if I wanted to go ahead and figure out what the value is, because it does say to go ahead and round our answer to 4 decimal places, this is going to be approximately equal to, and if we bring up the calculator again, it's going to be, let's do the math, and then notice the fraction at the very end. So if I just press left, it gives me a fraction template, and it's going to be common log 8 over, and then common log of 5. And if I go ahead and just press enter, notice it gives me 1.292, and then it would end with a 0, so I can really just say it's 1.292 for this example. And notice I did use the approximately equal to in this case, as well as I think I did it before, but regardless, since I'm rounding answers instead of using equal signs, that kind of squiggly looking equal sign, which is called approximately 2, is usually the best thing to use for these. The second one says to take the same log and go ahead and convert it to natural log, so I'm just going to actually type this into the calculator here in just a second just to show that it does truly equal the same thing. But again, it's going to be whatever the base is goes to the bottom. It wants natural log, so I'm going to use ln instead of log. So it's going to be the natural log of 5 on the bottom, and then whatever was inside would go on top inside of a natural log, so it would be natural log of 8 on top. And again, you could put parentheses around it, but I didn't on the previous example. I just want to kind of show that technically it does not matter when it comes to writing it, whether you have a parenthesis or not. So let's type it in. It should turn into the exact same answer. So I'm going to do the fraction thing again. So just press math, press left, and enter. And I'll just type in natural log of 8 in the numerator, over, and then natural log of 5 in the denominator. And when I press enter, notice it is the exact same value. So notice it would not matter if you switch to common logs or natural logs. We still get the same value regardless of 1.292 for this example. Alright, so now with regard to kind of the using of a calculator and plugging those things in, now there are some calculators that do allow you to actually just type in exactly as it looks and make it look like log base 5 of 8 in the previous example, so you wouldn't necessarily have to do the change of base, but the vast majority of calculators, I'm assuming that you guys probably have access to, do not have the ability to do that. So knowing the change of base formula is going to be relatively important when it comes to evaluating things, especially if I wanted to make a t-chart for something like this with log base 5 of x. Since log base 5 is not a button on our calculator, I would need to rethink of this if I wanted to type it in as maybe like natural log of x over the natural log of 5. Or you can even use common logs, that was a weird x, and call it the common log of x over the common log of 5. Regardless, it would still give you the ability to identify what the graph is if you had a graphing utility. But for this one, I'm going to go ahead and just kind of fall back to what are some of the common points that we should know. The common points, if we recall from a slide a lot earlier, were on a exponential, it would have been -1 and the reciprocal of the base. So for the inverse, it would be the reciprocal of the base paired with -1. So in this case, -1/5, common -1 should be 1 point on there. Normally an exponential would go through 0, 1, but this one should go through 1, 0. And then the next one is whatever the base is paired with 1, and then the next one after that is whatever the base squared is paired with 2. So notice this last one here is just a little bit too big for our grid, and by a little bit I mean a lot. So really it's just going to be the first 3 points that we could plot and then just kind of see what that turns into. So if I go to 1/5 common -1, that would be right about here-ish. The decimal one is always going to be just kind of a get it at least in the right ballpark. I do have a vertical asymptote. I guess I could mention that off to the side. There is a vertical asymptote that normally is supposed to be at x equals 0. So if I were to draw that on my grid, it would just be this vertical dashed line at the y-axis. So I know my graph's going to get close to that, but not cross it. 1, 0 would be right here, 5, 1 would be right here, and then 25, 2 would be way over off to the right of the screen. So this one, as far as the shape of the graph, will look something kind of like this. And if you kind of think in terms of why was this one so much different than the inverse of the 2 to the power of x from earlier, it's mainly the bigger the base is, the faster to the right technically these will go. So had this been a log base 2, it would have gone through 2, 1 instead of 5, 1. So as that base increases, kind of think in terms of this point right here. If that number is getting bigger, it's going further to the right, even though the y is only going up by 1. So the bigger the base, kind of the flatter it is, if you want to think of it that way. And technically the steeper it would be coming up as I get close to the y-axis. But this is going to be kind of our basis for this. We also could have done this with a t-chart, just to kind of mention how that would have worked. For this one, it would actually just be pick y values, and just think of this expression in exponential form, where it would be 5 raised to a power of y would equal the x value. So we could have done it that way, where 5 to the negative 1 is 1/5, 5 to the 0 is 1, 5 to the first is 5, and 5 to the second is 25. So notice it's actually filling in the left column instead of the right column. Still get the same ordered pairs without having to necessarily have the points memorized. But again, kind of the moral of the story here is if you do convert it to kind of an exponential form, you'll really want to just pick y values to solve for x's as opposed to picking x's and solving for y's. It just makes it a lot easier for these log functions to actually kind of work a little bit backwards. So, just like we had with exponentials, these logarithmic graphs, even though that one was basically just one of the parent functions, if we think in terms of can all of the transformations still hold true with graphs of these, absolutely they can. So each of these, we still kind of think of what's inside, what's outside. The inside is going to be anything that's within the parenthesis. The outside is basically anything that's in front or at the very end outside of the parentheses. So if we tried to describe this utilizing maybe what we know about transformations, we could go with what is the original function. So in other words, what is the x and the log base 5 of x? What is that list of numbers? Well, again, I could just plug in, I guess in this case it would be plugging in, think of our y values, so what would give me like -1 back as an answer, or what would give me 0 back as an answer, or 1 or 2. And if we go backwards, it would have been 1/5, 1, 5, and 25 were the points that I had from the previous slide. So I'm just going to take advantage of kind of keeping this together, and really I'm going to come up with what's going to happen for our new actual graph of this with regard to, I guess I'll call that f of x, not y, with regard to thinking about transformations. So this 2 that's in front is really going to do a vertical stretch, so that would be multiply y by 2. So that's going to be the first thing that I would need to make sure I accomplish. The -1 that's on the inside should be a shift to the right 1. So that means I should add 1 to the x's if I move to the right. And then the +3 that's at the end should move a graph up 3, so that's going to be changing a y value. So that would be the third thing I would do, where it would just be add 3 to the y's. So the y's I have to do in a specific order. I do have to do the multiplication before I do the addition. Still think in terms of order of operations. So I'm just going to kind of adjust each of these accordingly, just based on what they have. I'll start with the x's. The only thing that changes the x's was the second step, so I'm just going to add 1 to each of those x's. So 1/5 would turn into 6/5, or 1.2. 1, if I add 1 to it, would turn into 2. 5, if I add 1 to it, would turn into 6. And then 25, that's too big for my grid anyway. I'm not going to worry about that one. But technically it would turn into 26, I guess. May as well write it down. Now the y values I need to double and then add 3 to. So if I double -2, that would turn, or sorry, double -1, I get -2. But when I add 3 to that, -2 plus 3 would turn into +1. Go to the next one, 0, double that, I still get 0, but then add 3, that would turn into 3. And then the next one, 1 doubled is 2, add 3, that turns into 5. And then 2 doubled is 4, add 1, that would turn into, add 3. So, sorry, I kind of got a mental block there. So 2 doubled is 4, add 3, that gives me 7. So as we can see here, the stretch vertically by 2 is just kind of changing how fast my vertical is going to be changing. I do have a new vertical asymptote of x equals 1, so I'd have now a vertical dotted line that I would make sure I just approach, don't cross, and just go ahead and plot these points. So I've got 1.2, comma 1 would be right about here, 2, comma 3 would be right there, 6 comma 5 would be all the way over here, and then 26 comma 7 definitely too far for this grid. So this will start close to the vertical asymptote and then just start swooping to the right. So all log graphs should in general have something that would look very similar to what we just did right here. Next example we'll talk about is just what's the graph of that natural log function look like. So again, natural log is the same as doing log base e of x, which in exponential form I could really say this is really like e to the y equaling x. So when it comes to making a t-chart, if I said what's this really going to be if I plug in some y's, -1, 0, +1, maybe even +2, and just write these down as approximations as far as decimals are concerned, since e is not a very nice number. The 1 over the 2.72, because e to the -1 would really be like 1 over e, and 1 over e was approximately the 0.4. 0, well 0, if I were to have anything raised to a power of 0, it would equal 1. E to the power of 1 would be e, so that would be like 2.7-ish. And then let's see, what would e squared be approximately? That one comes back apparently close to like 7.4. So those would be like my original parent graph parts. For this though, I need to think in terms of where would those points actually be on our grid. So 0.4 would be a little bit over, and then -1 right there. 1, 0, 2.7 comma 1, so right about there. And 7.4 comma 2 would be just a little bit less than halfway right there. And again, still a vertical asymptote for this one since there was no shift. That is the y-axis, or x equals 0. So the graph of this one would go through those points. So notice it really does not look a whole lot different. It's just a matter of how fast it's going horizontally. That really changes as that base changes. So even though this had a base of e, which is 2.72, and the previous example had a base of 5, I believe, the base of 5, notice, made it grow horizontally faster than a base of e, but still generic shape of the graph still remains the same. It's just the points that it would be passing through that will be a little bit different. So if I were to use that same table as before, I'll go ahead and just, while it's somewhat fresh, go ahead and write it down. So it was -1, 0, 1, and 2, and I had 0.4, 1, 2.7, and then 7.4 were like the decimal approximations for those. This now I can think in terms of what should be happening based upon what I see. Well, I do see addition inside, so that should be a shift to the left, and then whatever the amount is. So in this case, left 3. I don't know what that just was. Sorry about that. So what that should do is essentially just affect the x values. So it would just be for my actual graph of f of x, my y values are going to remain the exact same. So the fact that that's going to be a -1, a 0, a 1, and a 2 is not going to change, but the x values that I have are going to decrease by 3. So if I did 0.4 and then subtracted 3 from it, I'd end up with a -2.6. If I take 1 and take away 3 from it, that should go to a -2. 2.7, if I subtract 3 from it, that should turn into like a -0.3. And then 7.4, if I subtract 3 from that, that actually would turn into 4.4. And our vertical asymptote that happened to be at x equals 0, now, because I've shifted to the left, should be at x equals -3. So I would first think to get that on my grid so I know what line I can't cross. And now let's go ahead and plot some points. So -2.6 comma -1 would be right about there. -2, 0 would be here. 0.3 and 1 would be right about there. And then 4.4 comma 2 would be right about there. And again, notice the shape of this graph really has not changed a whole lot. It was just now a little bit further to the left than the previous example was. And now on to our last example that we'll actually work through with this one, which is again just more graphing with this particular function. Let's go ahead and potentially rewrite this where it's a little bit more normal for that 3. I could say that this is negative 1/2 times the natural log of x, and then the plus 3, because it's positive, put at the end. So if I think in terms of what do each of these things do, this negative should reflect over the x-axis. The 1/2 that's in front, that really should be a vertical shrink, because again it's outside. So that's really going to divide my y values by 2. And then the plus 3 on the outside should be a shift up 3 places. So if we once again just take advantage of the table we've already made for the natural log function, which was -1, 0, 1, and 2, and the decimals I had were 0.4, 1, 2.7-ish, and 7.4-ish. That should give me at least a decent idea of what should happen. So if I think in terms of how should these things change for this function f of x, well, the x values, I feel like there's nothing inside, so the x values actually are going to remain the same at 0.4, 1, 2.7, and 7.4. But the y values definitely have some things that are changing. So the reflection and the shrink by 2, I can kind of combine those into one step. I could just say I'm going to divide everything by -2 and then add 3 to that result. So if I did -1 divided by -2, that would turn into positive 1/2, plus 3, that would turn into 3.5 or 3.5. If I take 0 and reflect it, and then or divide it by -2, it stays 0, but then add 3 to it, that would turn into 3. If I take 1, divide it by a -2, that would turn into a -1/2, but when I add 3 to that, that would turn into 2.5. And then 2 divided by a -2 would turn into a -1, and then if I add 3 to that, that would turn into a 2. So now notice I can go through all of the same steps as before. My vertical asymptote, I didn't have any horizontal shifts, so it should remain the y-axis, or at x equals 0. But I should now be able to plot these points. So 0.4 is now up at 3.5, so that would be like right about here. 1 is now at 3. 2.7 is now at 2.5. And then 7.4 all the way over, almost as far to the right as possible, is now at 2. So notice what's happening now is because of the reflection, it's now kind of an upside down logarithmic shape that then was shifted up. So again, you can plot it by using a t-chart like we're doing and then just affecting only the x's or the y's individually, or you could have physically actually pictured where that point is and just taken it on the journey by reflecting, then cutting it in half, and then adding 3. Just kind of depends on if you're more of a visual person or if you're more of a algebraic or numbers person. But regardless, hopefully you can find a strategy that will work for you. You should have more than enough to be able to practice in your homework, so hopefully by the end of the practice you feel confident with being able to do all of these graphs, no matter what the transformations have to be. But as always, if you have questions, just reach out and we can maybe work through more and more examples until it finally makes sense. But anyway, appreciate you guys taking the time watching the video. As always, if you have questions, just reach out and let us know. But I guess we will catch you guys next time.